How many of you are awake? So when I see this error message, there's quite a bit of terror related to it, right? The idea is that when you see your certificate has expired, you think of the worst case scenario. Your users can't access your services, other services can't access services, you don't know which certificate has expired. Let's acknowledge this. We've taken down the internet because our certificate has expired. A less known error message, and probably a less concerning error message, is that maybe your service's address and credentials have changed. Now, this is not as a big deal as a certificate expiring, but here's the key. They're changes. And the thing is, we're scared of changes to our system. We're scared of changes to our systems because sometimes we expect them not to change when we write our automation. We expect them not to change when we do something. And the reality is, well, systems change. And the result is that when your systems change, sometimes your services just end up failing. Now, this is the worst case scenario. Sometimes it's not this bad. But how do we think about change? And I think what's important to understand is how do you think about change in the context of security? Because sometimes in security, we think things don't need to change. We expect to secure our systems one way, and that's the way that it will always be. And with the certificate expiration, that's just one example in which your systems are going to update themselves. So the question is, how do you secure changing services and systems, but also improve their resilience? We've talked about this a lot today. You've probably heard it over and over and over and over. So right now, I'm going to do the same kind of talk track, but we're going to go very, very deep into two specific technologies. The first is a service mesh. A service mesh is an infrastructure layer that secures service registration and communication. It's OK if you're not as familiar with a service mesh, but the idea is that you're using proxies to secure communication from service to service. The second technology we're going to talk about is a secrets manager. As a solution, a secrets manager automates service identity and access. And you can imagine where I'm going with this. We're talking about Vault and Consul. Now, I wanted to put a big heart between the two for this talk, although they told me I couldn't put emojis in the title. So here we are. We're talking about Vault and Consul together. If you combine Vault and Consul, the idea is that you have the ability to use Vault to secure service communication with mutual authentication. And why is this important? It helps you automate it. It accounts for changing systems. But let's not stop there. Let's go the reverse direction, because why not? The relationship is symbiotic. It's mutual, remember? We're talking about mutual authentication. I figured it was appropriate to go the other direction, too. We're going to think about how you use Consul as a service mesh and a source of truth for your services to automate service authentication and authorization. So if you have a source of truth, and that source of truth is accounting for change, you can then automate any changes to your service authentication and authorization. We're going to dive into this in the form of a couple different ways. The first is certificates, right? I talked about that certificate example. We really narrowed down on it because there's just too many ways in which I could talk about Vault and Consul together. But specifically in the context of certificates, we are adding flexibility to certificates when we use a secrets manager to manage them. So you're going to see a lot of Vault PKI today. We're also automating the secret generation, where that's the other direction, right? So we're going to use Consul to automate secret generation in Vault. I'll show you a little bit more. And the overall benefit is that you're going to improve your system resilience as a result. So if you're able to do this, account for changes and use automation to do so, and let's say account for the events, right? We're not talking about accounting for changes that we're pushing declaratively anymore. We're also accounting for events, which are changes in our system. You can improve the overall resilience. And you're reducing your overall operational effort. So as a note, I talk about Vault and Consul together. And I'm going to get this question, so I'm going to address this right now. If you're using Vault and Consul, you're probably thinking Consul as a storage backend for Vault. I recommend you move away from that and think about using integrated storage for Vault. Because you're going to ask, why would I do this? This is a circular dependency. My Vault depends on Consul, and now we're saying that they're all depending on each other. So I'm just saying right now, reduce the circular dependency. Change it to an integrated storage backend for Vault, or if you're using Consul as a storage backend, choose a different Consul cluster that is not your service mesh. Please, please do that. So I'm just making this note before we start. All right, so let's take one example. Let's secure service communication with MTLS. you're not familiar with this, from a development standpoint, this means your services need certificates, right? So your services need certificates in order to communicate each other in an encrypted way. So let's talk about this one. We've heard a little bit about it. There was a release on it, quite a few Consul releases supporting this. But we're going to use Vault as a secrets backend for Consul. You've probably seen a Learn tutorial about it. You've seen a number of resources. We're going to come at it from the Vault perspective. Vault supports a number of Consul-related secrets. Some of these include TLS certificates for agents, tokens for access control lists, encryption keys for gossip, enterprise license if you're using Consul Enterprise, as well as agent configuration for snapshots. I'll pause for a moment so folks can take a picture of the slide, because this is a good list. I went through and I read the Helm chart, everyone. And then the next set of secrets that you're going to use are for your service mesh related to Consul. So the service mesh related to Consul involves 2 sets of TLS certificates. And the reason why I say 2 sets is that maybe the other one is for other types of traffic. But the main one you're going to be looking at is the TLS certificate for the service mesh, and that encrypts service-to-service communication. That enables MTLS for east-west traffic, so that's services that are in a cluster or in a Consul data center. You also have TLS certificates for Consul API Gateway. Yes, we're talking Consul API Gateway today. And what we're going to use it for is encrypting communication to services in the mesh, so it's an ingress, right? You're enabling TLS for north-south traffic. So we're talking about both these secrets. Now, let's talk about Vault, because we talked a lot about Consul, but we didn't actually talk about what in Vault supports Consul. In order for you to use Vault as a secrets backend for Consul, you need to use 2 secrets engines. Yes, just 2. The first is PKI, and what it will do is generate certificates for Consul. It handles certificate expiration automatically. This is magical. If all works well today, because in some ways I am more nervous than you are, my certificates should be rotating every 20 minutes during this demo. Hopefully it works, okay? The next thing is key value version 2. So key value version 2 stores and secures static secrets. This means the Consul gossip encryption key, the bootstrap token, etc. you can store in KV-v2. Now, one thing to notice is that it doesn't do this, it doesn't handle an automatic rotation from the Consul side, right? So you have to manually update parts of Consul from an operation perspective in order to rotate and accommodate for any rotated secrets on the KV side. So PKI is automatically handled, KV version 2 is not. We're going to talk about PKI today, and the really cool thing about PKI is if you dive underneath how Consul is actually referencing the secrets from PKI, you'll realize that it's actually the 3 different patterns that an application would use to access a secret from Vault. We'll go more on that later. Okay, so I'm going to switch to demo. Everybody, let's hope this all works. So to show you a little bit of what this looks like, I am using Kubernetes today. You can do some of this as a variant without Kubernetes. So I'll explain which parts you can do without Kubernetes and how you might do them. But first, you set up a Kubernetes auth method if you're using Kubernetes. This is my main auth method path. And what this will do is allow services using a service account in Kubernetes to connect to Vault and authenticate to Vault. The other thing that I've done is set up a bunch of secrets engines. So this is not necessarily maybe the number of secrets engines that you'll see, but I'll go through a few of them. The first is the Consul static secrets engine. One of the reasons why I set this up here with all of the bootstrap token and gossip encryption key, for example, is that I want to put it in one place. So if I have to manage it, I'm able to manage it under one secrets path. There are 7 PKI secrets engine mounts in here. So the first is for the service mesh, and you'll notice this PKI, and then you'll notice PKI intermediate. The PKI intermediate has to exist, and I'll explain a little bit more about that later. There's also a root, which is, again, another related to service mesh. There's the gateway root, the gateway intermediate. There's also the servers, so that's for servers and clients. So each of these exist. That's the initial thing you'll need to set up in Vault. Now, the way this works in Kubernetes specifically is that you can reference the Vault secrets backend in part of your Consul Helm chart. So in your Consul Helm chart, what you'll do is connect to all of these secrets engine paths. So for example, in the case of Connect CA is done in Consul. So the console configuration is actually a connect configuration. You can set up Vault as a CA provider in your agent config. And so this in Helm is mapping to that agent config. You'll set up the root PKI path as well as the intermediate one. The next thing is if you need to use a certificate to secure your cluster operations, so that's agent to agent, right? So that's specifically console itself, not necessarily the mesh. Use a different certificate. We are using a different certificate here. We are also setting up the ability to retrieve the bootstrap token as well as the gossip encryption key from the static key value store in Vault. All of these things get passed through the console Helm chart. If you're doing this by yourself and you don't want to use Kubernetes, you can use a combination of Vault agent as well as some of the internal configuration for the console agents in order to build this. Okay, so let's go back and I'll explain the next bit. Okay, so the first thing we're going to talk about is briefly TLS regarding this console servers. The TLS for console servers involves a couple things. Most of the things that you're going to see from the console documentation is going to recommend using, or not recommend, but use Vault to generate the root certificate or the root CA. Most of the time, this isn't the case. Most of the time, you get a CA, it's an offline root CA, and you should keep it offline from a security standpoint. So what you're going to need to do is set up Vault PKI secrets engine to generate several levels of intermediate certificates. And I'll go into that a little bit later. But in the case of this console servers and the console clients, it actually uses the Vault agent sidecar in Kubernetes. And it's the Vault agent sidecar that goes out to the PKI secrets engine and injects the CA as well as any certificate information to the console agent. So that's the first thing. So it's actually one pattern, right? So if you're developing an application, this is the first pattern you might consider, which is the Vault agent sidecar. It's going to retrieve information from Vault for you, write it out to a file. In this case, it's a certificate. So what I'm going to do is briefly switch back to this one. And I'll show you a little bit about what it looks like. The first thing is that I've set up 2 levels of intermediate certificates here. But more importantly, I'll show you what this looks like from the deployment standpoint. So if you notice, I have a lot of pods running in the same namespace just for the ease of use, but you'll probably separate this out in different Kubernetes namespaces. I'm going to grab the console server. And what we're going to do is retrieve information about the console server. I'm going to grep for the Vault HashiCorp.com annotation. And the reason why this is important is that if you're familiar with the Vault agent injector, what you're doing is adding an annotation in the Kubernetes deployment, and this will automatically inject the agent. This is the same thing that's happening with console. It's actually really interesting. We're even using our own patterns to inject secrets. And what's really interesting is that console as a system is written to reload these certificates. So it's dynamically reloading it, right? So the question that I get a lot is, if I'm doing dynamic secrets, how do I get my application to pick up the new set of secrets when they're revoked? This is how you have to do it. You have to update your application in order to handle a hot reload of this. So that's actually what console is doing. So you notice it's injecting the secret from server CA cert, et cetera. All right, so that's a brief note on the server certificates. But you're like, Rosemary, you talked a lot about service mesh. Why aren't we talking about the service mesh certificates? Well, we have to set that up a little bit. So I'll go forward. So service mesh is a little more complicated, similar approach. You're probably going to bring an offline root CA. You're probably not necessarily going to be using Vault to generate the root certificates for you. Or be a root CA itself. You're not necessarily going to do that. So you have to set up the intermediates. And in the case of the service mesh certificate authority, it is directly calling Vault. It's using an SDK to call Vault, right? So that's actually a second application pattern. Some of your applications might not want to use the agent injector. They might not want to use other methodologies. They want to directly call Vault. So this is actually one of those ways. And console, underneath it all, is written to handle a reload of those certificates if they expire. So actually, it will reload when the certificate expires. OK, a little diversion. In the Connect CA case, I have 3 levels of intermediate certificates and certificate authorities. Why? Well, it turns out that most service meshes, if you haven't used them, use something called SPIFFE. So SPIFFE is a way in order for you to have compliant workload identification across your Kubernetes cluster. In order for you to comply with SPIFFE, you need to inject it into your certificates. So it turns out that you can't do it at the root CA level. After all, it's an offline root. You're getting it from somewhere else. You can't do it at the first level intermediate, but you can do it at the second and third level intermediates with Vault. So if you are doing an offline root for a service mesh, you need at least 3 levels. You could probably do away with more. But the result is that we're actually using the level 2 and level 3 intermediate CAs to generate a root certificate as well as an intermediate certificate for the service mesh. That's important to know. Took me a while to figure that part out. So let's explain a little bit further about what that looks like. So let's take a look at how this is set up. So the reason why I recommend you use the offline root from a security standpoint is that you want to keep the key offline. And I've generated a self-signed certificate in which it is an offline root. So if I examine, I'll show you a little bit about this one. There's a lot of Terraform. I'm sorry, everybody. But there's a connect CA, and I have a root, and I have an intermediate. And the root has the key, the private key, as well as the certificate. And I actually have the intermediate as well. And the way you generate the intermediate CA from that offline root is that you do have to set up an initial secrets engine for PKI. That's what I do here. You also have to generate an intermediate cert request. So in the case of the Vault API, this is something that's generating the certificate request. And remember what I mentioned before. You have to pass a URI that says this is a SPIFFE compliant workload. So I'm passing a SPIFFE URI here. The trusted domain in the case of Consul is the Consul cluster ID.consul. So this has to be passed in order for Consul to recognize that the certificate is able to communicate within Kubernetes. Now, it's not required. You can do without it. But if you're using API Gateway, it's probably recommended that you should include this. So the next thing you're going to have to do is generate a certificate signing request. And you can do that from Vault. So Vault, you can call and say, give me a certificate signing request, and you'll download that locally. And after locally signing it, then you have to upload the certificate and CA and everything else back up into Vault. So that's why you set this intermediate set signed. The other important thing to know about when you do this with a service mesh for the offline root, you must have the entire CA chain defined, which means you must go from the intermediate down to the root. So if you do not have this, the Consul service mesh cannot validate that it is a valid certificate, right? So it needs the entire CA chain. So that's why you need to include this. The next is I add more intermediate certificates. So you'll notice the same pattern. Where I'm generating an intermediate certificate request, I'm using the root to sign it, and I'm repeating it over and over. The difference, however, with the second level CA, intermediate CA, is that I'm signing it with my level 1 intermediate. So I'm pretending the level 1 is my root, and I'm signing it for the intermediate. So I'm not using the offline root anymore. And what this means is that basically I'm able to use Vault to issue certificates against the intermediate certificate authorities. But however, the same pattern applies. Make sure you specify your URI sans, as well as these files. You have to upload them, make sure you have the entire certificate chain, et cetera. So this process repeats again for the third level intermediate. So if you have multiple levels of intermediates, maybe you have one and you're then planning to do level 8, 9, and 10 in Vault, then this is the path that you would take. OK, so what does this look like in practice? Well, if I call the Consul API, what you'll notice is that it has a Vault as a primary certificate authority here. So Vault CA primary cert. So this means that I've set it up to use Vault as a CA provider. The other important thing that I've done is, well, now it's just retrieved a root cert as well as the intermediate certs. And just to show you what I mean by the SPIFFE situation, if you retrieve the cert that has been generated and passed to Consul, you want to make sure that the subject alternative name is including that SPIFFE URI. So this is the trusted domain that is the Consul cluster ID.consul. So this needs to be in here in order for the certificate to be properly validated. OK. So there's a couple things. If you're interested in learning more about how this is configured, I have a repository set up. And it's also including a giant script in which it does the offline signing, its sequence, et cetera. So you can examine how it's doing the signing and then how it's reloading them into Terraform as well, if you're interested. OK. So what does this look like? Let me just swap this way. OK. So now let's talk about API Gateway. That was Service Mesh. Service Mesh will handle the rotation by itself. if your root changes, if your intermediate expires, which it has done a couple of times already, Consul will automatically handle the reload, which is really nice. But what happens with API Gateway? API Gateway is currently available on Kubernetes specifically. And what's interesting about API Gateway on Kubernetes for Consul is that it uses the gateway spec for Kubernetes. You can't inject Vault agent into it, right? If you've ever tried to inject something into a CRD or a CR or a custom resource definition, it just doesn't quite accommodate for it. So how do you actually get the gateway to pick up the certificate? Well, we're going to set up the same pattern. We're going to use an offline root CA, set up the PKI secrets engine with a root, and then second level intermediate. And what we're going to do is use the Vault CSI provider. If you're not familiar with the Secret Store CSI driver project, the idea is that you're able to use the Vault CSI driver in order to retrieve information from Vault and inject it into a volume, right? So you mount it as a volume. But there's also a side feature to it. You can inject it as a Kubernetes secret. You can set up something called sync as secret. And what it will do is retrieve the secret from Vault, write it out to a volume and a Kubernetes secret, which means that any custom resource that cannot use the injector can read it from the Kubernetes secret. And that's what we're doing with Consul API Gateway today. So that one's a little more detailed. I'll show you a little bit of what happened here. Okay, so you're wondering, why did we include the spiffy URIs? The spiffy URIs, do they need to be there? Actually, yeah, sort of, because the API Gateway needs to validate the spiffy URIs in order for it to properly connect, right? So the thing is that you can do it without the spiffy URIs for the service mesh, but API Gateway may not be too happy with that. So we are using a second level intermediate for the gateway. We've set up the PKI the same way. So same way, sign, download the intermediate certificate signing request, sign with root, upload back online. Same patterns over and over and over again. And again, we include the certificate chain as well. So we're using that certificate. The important thing to know about the secret provider class, I'll actually show you the Helm chart. Let's go back to that for a second. One second. Here we go. OK, let's go to Helm chart. So this is the Helm chart release, or Helm release for Vault and CSI. In order for you to do CSI Secret Store CSI driver, as well as the Vault CSI provider, it's a two-step process. You need an initial Helm release with the CSI driver. This is the driver that mounts the volumes, right? And you'll need to turn two things on. You'll need to change two settings. The enable rotation, secret rotation must be true, and the sync secret must be enabled as well. Sync secret is where you're allowing a CSI driver to synchronize it to a Kubernetes secret. So you must enable this. The second thing you'll need to do with Vault is set CSI enabled to true. So what this means is it will deploy the Vault CSI provider. OK, so let's check out what this looks like. So if I get my pods in my kube system, CSI, what grabs for CSI? The CSI Secret Store driver, it's a mouthful, sorry everybody, but if you're using the Secret Store CSI driver, this will deploy in the kube system namespace by default. It does need access to host path because it is mounting volumes. So keep that in mind. If you're running something like OpenShift or a particularly restricted Kubernetes cluster, you do have to be cautious of deploying the CSI driver, right? You have to add additional permissions to it. The other thing is the Vault CSI provider. So let's check out the Vault CSI provider. It's deployed into my default namespace for now, although you could deploy it into a Vault namespace. So you have the Vault CSI provider running. The important construct you'll need to know about in the case of the Vault CSI provider and the CSI Secret Store driver is the secret provider class. So the secret provider class is a way for you to define exactly how you're going to retrieve the secret from Vault and inject it into a Kubernetes secret. So let's get that one, and I'll show you what it looks like. So a couple things that you have to define here. The secret provider class allows you to specify the kind of object name that you want to define, as well as the method you need to use for Vault. The key is that if you've looked at the PKI Secrets Engine Vault API, you must use a post method, an HTTP post method, in order to issue a certificate. So what I've done here is I've specified the secret path is the second level intermediate CA in Vault, and I'm issuing a post to it. Now, with this post call, I also have to specify some configurations. If you try to issue this call without specifying a common name, Vault will return an error message saying, I expect you to give me a common name. So in this case, I've chosen a common name, and the result actually in the gateway setup is that I've specified that I've allowed domains, let's say from hashiconf.example.com. So you can set it up in the Vault side, the PKI secrets engine side, what domains you want to issue the certificate under, and you pass the common name regarding with the gateway through here. The other thing is that it's retrieving the certificate and private key. If you want to map this to a Kubernetes secret, the TLS type, you need a certificate and a private key. Very important to remember. So we're diving deep into this. I know everybody's like, oh, is this over yet? But the idea is that no, because certificates never stop, right? So a lot of this here is configuration, but after you get past this initial configuration, a lot of the maintenance after this is not going to necessarily have an impact. So the next thing you'll need to do in the secret provider class is the secret object. This is what signals to CSI that it should write it as a Kubernetes secret. If you don't include this particular section, the Vault CSI provider will not know to write it to a Kubernetes secret. So you have to tell it which Kubernetes secret is, like console API gateway, CA cert, TLS.cert, TLS.key. For those who are more Kubernetes knowledgeable, this might be already familiar to you. But just to show you that I'm not joking, and it does exist, I'll try console gateway cert. So let's get the secrets. And I'm not going to print it out because it's base 64 encoded, and I don't want someone trying to go back and getting my certificates, even though it expires in like 20 minutes anyway. But regardless, you'll notice that there's this console API gateway cert Kubernetes secret that's been generated from that. The reason why this exists is that I have a pod that I've deployed called the secret store inline, or not pod, but deployment. This secret store inline is a deployment that I've written in order to signal, right, because Kubernetes needs events. It signals to the CSI driver, I want this secret synchronized. Otherwise, it won't do it. You could create the secret provider class and never find the secret. So in order for this to work, you do need some kind of busybox or other sort of deployment running in order to signal to the CSI driver to retrieve the information from Vault in the first place. So I've defined this in a very straightforward way in that there's not too much information in it. You can use a pod that just sort of runs whatever image, secure image you're going to use. But the idea is that what it needs is, at the very least, let's grab this. It needs this CSI volume driver attribute. So you need to specify this, otherwise you will not get a Kubernetes secret under this model. And with that, I've also specified in the gateway, let's see, let's make sure my gateway's up. So I have a console API gateway up. Gateway, API gateway. What this means is that in my custom resource, gateway custom resource, I can set HTTPS available, right? So port 443. But more importantly, I can set a certificate reference. This means I'm referencing the Kubernetes secret. I have no agent injector. I have no way to inject or annotate, right? So what I'm doing instead is referencing the certificate. And that's what's important. So here, you'll notice that it is theoretically running. After I create an HTTP route in Kubernetes, this HTTP route object basically says, I'm going to forward everything to my Nginx service and use a path prefix of all. I should theoretically have a demo application running. This is our demo application. You might have seen it a few times. But actually, I'll show you something fun. It says the certificate's not valid because it's self-signed. But if you're using an offline, a not self-signed offline root CA that was officially issued, this wouldn't necessarily be an issue. But you'll notice that it's kind of small to see, but I'll read it out loud. It says that the certificate has a common name of gateway HashiConf example.com. This was issued by Vault. It's issued console API gateway CA2 v1.1. That means I'm using my second level intermediate, and it's expiring in roughly 5 minutes, 10 minutes, something like that. But it's been expired every 20 minutes or so. And so you'll notice all of this specification I put into Vault in the first place. So we can ignore that for now because it's a self-signed certificate. But the idea is that now I'm doing this over HTTPS. I don't need to reload the certificate because CSI drivers and CSI providers are already handling all of this for me. I don't have to do anything I don't have to control when it's revoking, when it's expiring. Vault itself is handling the revocation and then issuing a new certificate every time it expires. So this is all getting handled. And I don't have to worry about that. And in fact, just to show you the fact that the certificate is still expiring, even for Consul, if my internet will load, Consul itself is secured in the same exact way, remember. And so you'll notice that I issue the certificate to server.dc1.consul. So this is for cluster operations. And it will also expire in probably about, well, this one expires in about 15 minutes, so it just expired. And the idea is that here, again, I'm not necessarily changing anything. I don't have to go in and do the rotation. Consul's handling and picking up the new certificates and getting them issued by Vault. So all this is done. Okay, so one last thing. Go forward. All right, I talked about the second part of this, right? I went really far into the first part, using Vault to secure Consul. But we're going to go the other direction now. So sorry, everybody, we're just going to shift, turn the car around a bit. But the reason why I came across this was I was running a database on Kubernetes, and I was really tired of this, because what happened was that I guess I set up the database improperly in some ways, but every time I destroyed the database pod for some reason or another, and it created a new one, well, my Vault secrets engine couldn't issue credentials anymore, because the old one, it was referencing the old database, not the new one. Furthermore, it's not like I'm going to use the same password for the database in the previous one as the new one. Ideally, I don't want to use the same username and password. After all, I'm using Vault to issue credentials dynamically, so why wouldn't I want a new username and new password for a new database? And the real issue was that my application could not find the new pod. It was wondering where it was, it couldn't access the database, and the application actually kept throwing errors on me. So I said, okay, I'm getting really tired of this. I don't want to declaratively run Terraform because I realized that the application reloaded and the database reloaded. I don't want to do this. So instead, I introduced something else, because why not automate everything while you're at it? Instead, I decided I'd look at Consul Terraform Sync, because Consul Terraform Sync has the ability to take information about a service from Consul, run a Terraform module in response, and then update the target API of your choice. So in this case, I decided, why not use this to automatically update my secrets engine Vault so that I don't have to remember the database changed. So the way it works is that I have a database that's an external service in Consul. Now, this could work as a pod too. That's OK. You could do it as a pod. You could do it as any other service. But I register this as an external service in Consul because I'm using a managed database. You'll notice that it is going to register its information to Consul. So it's not part of the service mesh, but for those who are familiar with Consul, it is using a terminating gateway to reach out to a managed database. And Consul Terraform Sync will read the information from Consul about that database, contact Vault, and will create a database secrets engine, role, policy, and Kubernetes auth method for that specific database. The side effect to this means that I can use my application to retrieve the database secret from Vault. Now you're like, oh, this is a little dangerous. Like you're using Consul to configure a database secrets engine, and then now an application can access it. I will go into a little bit of how you might think about segmenting this away, making sure you restrict it a bit. But the idea is that you're dynamically configuring a database secrets engine, whether or not that service changes in Consul, right? So Consul Terraform Sync is handling that event for you. Now, there's some complexities to this. I'm going to just tell you a little bit about these complexities. If you are familiar with Consul Terraform Sync, you do need a module in order to use it. So let's take a look at the module. Let me pull this up. Kubernetes dynamo. OK, so I'm deploying Consul Terraform Sync on Kubernetes. You could deploy Consul Terraform Sync as any kind of daemon that you want. But in this case, I'm using it on Kubernetes because it's easy, and it needs access to Consul. And I wanted to make sure my Consul was locked down. So it's accessing the Consul server that I have. This is where my database is already registered. I'll even pull it up and show you. You'll notice there's my database. My database is registered. I'll even show you the address right here. So there's my address, right? And in this case, I'm referencing the Consul server at that address. And I'm registering Consul Terraform Sync. This was out in 0.6. But I'm registering Consul Terraform Sync as its own service in Consul so I can monitor it. As for Terraform itself, I do pass in some information about Terraform, like the Terraform provider's Vault. I also specify and built my own Terraform CTS module here. And the CTS module is really, really well scoped because I really only want it to do one thing, and that's configure database secrets engine role policy auth method. That's all I want it to do. I don't want it to do more. So in this case, I'm going to specify a task definition, and you'll notice there's a variable files, terraform.tfvars. You'll wonder what is in this, and I'll explain that. But my condition is going to monitor on the services called database. So that's the important thing. I'm writing this to a config map, which I'll mount to the Kubernetes deployment for CTS. All right, so everybody ready to get even more confused? I am using the Vault Agent Injector to get secrets about the database to configure the database secrets engine. So this is getting very, very complicated, but at the end of the day, it's important to recognize that all of my secrets are managed by Vault, including the database admin password and username, which means I can use Vault Agent Injector to inject it into Consul Terraform sync so Terraform can run properly. So here, I have a terraform.tfvars file. I'm once again using the Agent Injector to template a terraform.tfvars file out. And what this is doing is setting up all the variables I need. I'm setting it up for my product application. I'm using the Postgres username and password that is statically defined in Vault. So this is the admin password. Vault does need it in order to configure a database secrets engine properly. And I'm also putting together the service account names and namespaces. So when you specify the Kubernetes auth method, you need to tell it exactly which service account it is bound to. You don't want it to give it to every service account. Please don't do that. Do it to the specific application that needs access to that secret. So that's what I'm doing here. The other thing that I'm doing, and this is a trick here, it's important to know, if you're doing the Vault Agent Injector and you're retrieving a static secret, you can write it out to a file, right? And this file could be in the form of environment variables. And that's what I'm doing here. Here, Consul Terraform sync needs some information about Vault. It needs the Consul HTTP token, right? So I have not set up the Consul Kubernetes auth method for CTS in this situation. But in this, for CTS to run, for the module itself, it needs the Vault address, and CTS needs the Consul HTTP token. I am exporting them as environment variables and templating them out to a file. And the reason why is that when you use the Vault Agent Injector, it's a file-based secrets injection approach. If your app expects environment variables, it doesn't know what to do, right? Because it's a file. So here's the trick that I learned. You can override the entry point. And what you'll do is you'll override the entry point and pass in a nice little note to source those environment variables from the file the agent injector wrote. So this will source it from Vault address and Consul HTTP token. And then what I'm doing is exporting a Vault token. You'll notice you're asking, what is this Vault token? Well, every time Vault agent runs, it generates a token that you can use for other operations. So here we are. Here's another token. This is a child token from the original Consul Terraform sync service account token. So this is getting more complicated, but if you have questions, you are always welcome to ask. And the other thing you'll have to do in this situation is the original entry point, because you overwrote it, you need to pass it back in. So this is where this is the last statement here. This is the original entry point for the container image. And what I'm doing here is effectively anything that has to do with the Consul Terraform sync config itself is a config map, so I'm adding that here. So Consul Terraform sync does run as a deployment. In the case of CTS, accessing Vault, as I mentioned before, seems a little dangerous. You're like, you're letting it configure all the database secrets engines. No, please don't do that. Yes, please do not do that. What we're doing instead is limiting what CTS can access, just like an application would in the case of Vault. So CTS can access the Postgres database admin credentials so that it can set up the initial connection string. It can access the CTS, the Consul token and Vault address. It can create a child token. This is the permission for the policy in Vault to allow the CTS service account to create the child token. And you can allow CTS to get a list of secrets engine. You know, in terms of reading the secrets engine, fine, you can read it. But if you're going to do this kind of automation, tell it to go to a different mount path. Don't just expect it to go to every single mount path and add a new secrets engine mount to it. So instead, I am localizing it to a database path. So CTS can only create secrets engines at this path. and that's why I'm limiting that further. You could limit it even further by segmenting them in Vault namespaces if you wanted to on the enterprise version, or HCP Vault. But the idea is that just make sure that not every single service account and every single part of CTS has access to everything in Vault. Make sure you're segmenting those paths correctly and putting the right policy in place. And finally, CTS needs to set up the database secrets engine. It also needs to set up the ACL policies. It also needs to set up the Kubernetes auth method. And actually, this is where I ran into a problem. It turns out that if you are going to set up the Kubernetes auth method in Kubernetes using Terraform, you need to add a couple permissions. And so one of those things you need to add is a secrets writer permission. So in order for something in Kubernetes to write out to it, it does need to have additional permissions. So these are some of the permissions you might need. Regardless, you can tell that CTS is running. I'll get the console Terraform sync. You'll tell CTS is running. It's one of the pods. You know, it's pretty much there. And then if I grab the logs for it, I've turned on the Terraform logs, but you'll notice that it did indeed create a database secrets engine, an auth method, role, and policy in place. So all of this was reflected. And if I read from the config, you'll notice that this is the URL that console Terraform sync retrieved from console and synchronized. So anytime this service changes, console Terraform sync will run in response and update the secrets engine. And surprisingly, it updates without disruption, which is actually pretty cool. And then instead, this allows the product service that I have running to retrieve this pretty seamlessly. So if this is updated, for the most part, because of console's resolution, the service just pretty much just reads it from the database and expects it to be the same URL, et cetera. So nothing changes. For the most part, I'm pretty much hands-off. So I've changed this twice today, and so far it hasn't done anything. So I waited for it to break. But the idea is that this URL, if it does change, or if you're using a database pod, you don't have to worry too much. All right. So I don't have too much time left. So let's recap for a second. We talked today a lot about certificates. But what I omitted was ACL tokens. Vault 1.11 has a console secrets engine that you can use to issue service and node identity tokens. Very cool. But there are a lot of things you could do from Vault to issue and create console ACL tokens specifically. And in the reverse direction, we talked about service identity. So we talked about using console Terraform sync to retrieve services from console behaving as a source of truth, and then synchronizing it to Vault secrets engines. But I didn't really cover intentions. Actually, you can kind of think about the way that intentions work with Vault as well. So you should think about how you're allowing services to connect to each other, but also, more importantly, how services might connect to Vault, especially if you decide to put Vault as part of your mesh. There are some tricks there. But the point about this whole talk is that within all of these technical implementations, all of this detail, Vault and console work together to be more secure. And the point is that you can be more secure without necessarily adding additional manual effort. So yes, you're putting in the initial investment to do all this automation, but then after that, the maintenance itself is handled by the application, whether it be Vault or console. So in conclusion, your certificate has been rotated. Everybody is happy. I'm happy. My demo worked. No one saw an expired certificate, right, other than the one that was not authorized. But it has been rotated, so we're all feeling a little better. The service's address and credentials have been updated, so I get a new set of credentials anytime my database changes, for example, which I'm pretty happy about, so I can just let this run all day if I wanted to. And all my services are still working, which I'm really glad for. Now, if you want to learn more, which this is just the tip of the iceberg in terms of technical implementation, you can learn more about Vault and console in our documentation. Anything that you need to know about something outside of Kubernetes, feel free to ask, but the idea is a lot of these map to Vault Agent as well as to console's Vault CA provider. And if you want to try this yourself, I do have code available. So if you want to dig through my Terraform and you want to understand how to use the offline root CAs in the context of every single certificate related to console, you're more than welcome to take a look at the code. If you find anything, just let me know. There's a little bit of everything in this code base, and you can explore and understand how you can use Vault and console together. Thank you.